are 6 rational exponents. So we talked about rational expressions, you know about rational numbers. Now we're going to deal with rational exponents, which rational exponent just means you have rational numbers as the exponent, or you can have a fraction as an exponent. Before we really get into that, let's just take a step back and look at a couple things about exponents. So first of all, let's look at negative exponents. So negative exponents, if you have a to the negative n, remember that that just means 1 over a to the n. So that's all a negative exponent is telling you. It's just saying, well, put it in the opposite part of the fraction or rational expression. If it's in the numerator, move it into the denominator. If it's the denominator, move it into the numerator. Okay? So if we have 3 to the negative 2, that's 1 over 3 to the 2, or 3 squared, which is just 1/9. So pretty straightforward, but just a reminder of that. Recognize too with that, since it's, like I said, you just take if it's in the denominator, move it into the numerator. If it's in the numerator, move it into the denominator. It also has the effect, if you have a over b to the negative n, that can be rewritten as b over a to the n. And remember, that's the same as saying b to the n over a to the n, just to be complete in our relationships here. But if you have a fraction or a rational expression and it's all raised to a negative power, then you can just take the reciprocal of that fraction or rational expression and raise it to a positive power. So a very simple way of doing it. You don't have to break it down a piece at a time and deal with it that way. Now remember, the quotient rule tells us that if we have a to the m divided by a to the n, that is equal to a to the to the m minus n. A to the m minus n. It's going to be the difference of those exponents if we have the same base. Well, if we think about that and what we just said here, well, if we have a to the 0, isn't a to the 0 1? So a to the 0 divided by a to the n, a to the 0 divided by a to the n, that's the same thing. Any number raised to the 0th power is 1. That's equal to a to the 0 minus n, or a to the negative n. Sorry, I left off my negative, because I was trying to get back over here and say a to the negative n. So that's really what's happening there. And you can even look at the quotient rule and look at it and say, well, what's a to the 0? Well, a to the 0 is equal to 1. Well, the quotient rule, if we say a to the 5 over a to the 5, that's equal to a to the 5 minus 5 is equal to a to the 0. But if you have a to the 5 over a to the 5, isn't that equal to 1? So the quotient, we start to see these things come together, and using one rule, we can verify another rule, which is really nice. But now, knowing about this quotient rule, and knowing about negative exponents, and knowing that we can take the reciprocal of a rational expression, or a fraction if it has a negative exponent, then that can help us in simplifying some of our rational expressions. What if I have 27 x cubed y to the negative 3 z to the 1 over x squared y to the fifth z to the negative 4. And I want to simplify this. Well, we can use the quotient rule and we can simplify the constant parts of it. 27 over 6. We see a common factor of 3, so we can turn that into 9 over 2. So 9 over 2. And then we can look at x cubed over x squared. 3 minus 2 is 1. X. Y to the negative 3 over y to the fifth. Negative 3 minus 5 is negative 8. So y to the negative 8. And then z to the 1. I don't know why I put a 1 there. But z to the 1 over z to the negative 4. 1 minus negative 4 is 1 plus 4, so 5. So z to the fifth. And if we were fully simplifying this, that did get us out to this thing where you could say, okay, well, isn't that 9 halves xy to the negative 8 z to the fifth? You could say that, but we do like to have positive exponents. So if we were simplifying this, we really should move this into the denominator. So we say it's 9x z to the fifth over 2y to the eighth. That's our optimal way of writing it. We don't like negative exponents, so if we can get rid of them, we generally do. And many times you'll get told to do problems and it'll say, rewrite this with all positive exponents. So I could have given you this right here and said, rewrite it with all positive exponents, in which case you would have to bring it to that point right there. This would not be good enough. So that's simplifying some rational expressions where you have negative exponents and using the quotient rule. So continuing on with that, well, let's get to where we actually are dealing with rational exponents, because these aren't rational exponents, these are integer exponents. Rational exponents are the ones where we have an integer over an integer as the exponent. So let's get into what that means. Well, here I'm going to put it into something basic of a to the 1 over n. So we have a to the 1 over n. Now we have an exponent that is a fraction. N is in the denominator of this. When you have a base raised to a rational exponent, the denominator of that exponent represents a radical of that index. So a to the 1 over n is the same as saying the nth root of a. So remember, a to the negative n was the same as saying 1 over a to the n. A to the 1 over n is the same as saying the nth root of a. And if you think about it, that should kind of make sense, because what happens if I have a to the n over n? Well, n over n is what? 1, right? Any number divided by itself is 1. So a to the n over n is going to give you a to the 1, or a. Well, if 1 over n is the nth root of a, what's going to reverse that process? The nth root of a. What's going to reverse that is raising it to the nth power. If you take the nth root of something and then raise it to the nth power, the nth index and the nth root cancel each other out, and you end up with the original value. So that leads to our next one, which is that a to the m over n is equal to the nth root of a to the m, which is equal to the nth root of a raised to the m. It doesn't matter whether we take the root first and then we raise it to the power, or if we take the power first and then we take the nth root of it. It's the same thing. So if we have a to the m over n, we can rewrite that as the nth root of a to the m, or as the nth root of a raised to the m. So if I have t to the 5/2, we can rewrite that as t, we can either do t to the 5th, the square root of that, I don't have to put a 2 in there, right? Because for when you have the square root, that index is 2, it's assumed. Or we can say the square root of t raised to the 5th. So that can be really handy to us when we're dealing with rational expressions. Let's take a look at one and see. (81 to the 3/4). Well, what does that mean? That 3/4 tells us, well, and I'm going to state this so that we recognize that, because we kind of get caught in formulas sometimes and we don't recognize what's really happening. Basically, what it tells us is if we have a rational exponent, the numerator of that exponent is the power, the denominator of that exponent is the index of the root. So this is really saying 81 cubed, the 4th root of that, or the 4th root of 81 cubed. And we can use either way, it just depends on how we feel more comfortable, or which one will make life easier. Now in this particular case, I look at this and I go 81 cubed. Ugh. That does not look like a quick, easy number. And then to find the 4th root of that doesn't sound fun either. Now I could take, obviously 4th root, then couldn't I take the square root and then the square root? But 4th root, this doesn't look pretty to me. 81 to the 3rd. Just gonna grab my calculator here to get that number. 81 to the 3rd is 531,441. Wow, do I really want to deal with 500,000? Not when I see this, the 4th root of 81. The 4th root of 81 is 3. Cubed, right? The 4th root of 81 is 3, cube it, 3 times 3 is 9 times 3 is 27. Whereas here, 81 cubed came out to be 531,441, the 4th root of that. Whew. I'm definitely not doing that one in my head. This one I could. So we use whatever is easier. Now, of course, if I have that number, like I said, I take the square root and I take the square root, then I get the same answer. It's 27. But that's because I recognize that the 4th root is nice and balanced, so I can take the square root of it and then the square root of it. The square root of if I take the 4th root, it's really I can take the square root of this number and then I have the square root of that. But you have to recognize that to be able to use it. So definitely easier at points to do it one way as opposed to another way. But you can choose to use either one that you want. Well, what if you have, I don't know, let's come up with something good. How about 0 to the 1 over n? 0 to the 1 over n. Well, what is that? Well, 1 over n, that means it's the nth root of 0. Well, what's the nth root of 0? Well, what is an nth root saying? It's saying what number multiplied together that many times gives you that value. Obviously, 0. 0 can be multiplied together as many times as you want, and you're still going to get 0. So the nth root of 0 is always equal to 0. So therefore, the 0 to the 1 over n is always equal to 0. So you can keep that in mind in case you run into that somewhere. What if we have $25 to the 1/2? 25 to the 1/2, well, what's this tell us? Well, this raises it to a power of 1, which doesn't do anything, and we're taking the second root, or the square root of it, so that's the square root of 25 is equal to 5. Now, some of you may say, but wait, Mr. Davis, is that really correct? Couldn't that be -5? Because -5 times -5 gives me 25. And the answer is yes, it could. And when you're solving polynomials and when you're dealing with the quadratic formula and things of that sort, by all means you have to take into account the plus or minus. But in general, we accept the square root, or I should say, the root of any even index, nth root of some value, where n is even. Then we accept the correct answer as being the positive root. So the square root of 25, n is equal to 2, n is even, then we accept it as being the positive root, so positive 5. If n is odd, then we can deal with a positive or a negative root. Right? If we have this, let's go -27 to the 1/3. That's the cubed root of -27. Now, before you panic, think about what you're looking at. Remember, if you have an even number root and you have a negative sign inside the radical, then you're going to be dealing with imaginary numbers. But if you have an odd index, an odd root, cubed root, fifth root, seventh root, etc., then you can have a negative value in there and get a real result. That's going to be -3. -3 cubed is -27. Why does that happen? Think back to the basics. Even root multiplied, numbers with the same sign together or an even number of values with the same sign together, you're always going to get a positive result. Whereas with an odd root, if you have an odd number of negative values that you're multiplying together, you're going to get an odd result. If you have an odd number of if you're multiplying an odd number of positive values together, you're going to get a positive result. So this could be positive or negative depending on that. So yes, you can have a negative inside that radical. So just keep that in mind. But that's not as far as we go. So just move out of frame for a moment, come back in. Let's look back again, I'm just going to put my calculator out of the way. Let's look back again at some of our basic laws of exponents that we know. So I'm just going to do a little summary here. So we have the product rule, right? A to the m times a to the n is equal to a to the m plus n. We have the quotient rule. A to the m divided by a to the n is equal to a to the m minus n. Okay. We have the negative exponent rule. A to the negative n is equal to 1 over a to the n. We have the power rule. A to the m raised to the n is equal to a to the m times n. Okay, so we've got these different rules. We have another power rule. A over b to the n is equal to a to the n over b to the n. Another one of our power rules, a times b to the n is equal to a to the n, b to the n. Right? So we have all these different rules that come together for us, and then we have a to the m over n is equal to the nth root of a to the m, or the nth root of a raised to the m. So we got a whole bunch of rules that we use when working with exponents. So let's put some of them to use. And I didn't even include the whole a to the 0 is equal to 1, unless where a is not equal to 0, and 0 raised to any power is equal to 0 as long as the power is not equal to 0, and all those other things. So how can we put these to use? Well, what if we do something like 100 to the 3 halves times 16 to the negative 3/4. So what all is that doing to us? Well, we can look at it. First of all, we see a negative exponent. So I can look at that and say, okay, well, I can move that into a denominator. So I can call this 100 to the 3 halves over 16 to the 3/4. So I can start there. Notice that these are separate bases, so don't try doing anything like canceling out powers, okay? They're separate bases. But now we look at this and go, well, wait. Well, that's square root, that's cubing, that's 4th root, that's cubing. Well, square root's easy to deal with, but I'm just going to write these as, so the square root, I don't need the 2 in that. Square root of 100 raised to the 3 And then we got 16 to the 34. So the fourth root of 16 raised to the 3. Well, actually, we do have that rule. A over b to the r is equal, or n is equal to a to the n over b to the n, right? So we can pull that cubed out if we want. So we can say the square root of 100 over the fourth root of 16, all of that cubed. Now, remember when you're dealing with these that there are any number of roots that you could choose. You could have chosen to do these as 100 cubed and then take the square root of that. 16 cubed and take the fourth root of that. You don't have to pull this out here. You could treat this first and then just cube it. Treat this first and cube it. So just remember, just because I choose to use one route to get there doesn't mean that's the only route that you can use to get there. So now I look at this, well, what's the square root of 100? Well, I probably should have done that, right? That's pretty easy. So square root of 100 is obviously 10. The fourth root of 16, well, luckily that's an easy one for me. That's 2 times 2 times 2 times 2 is 16. So we have 2. All of this raised to the 3. Well, maybe this wasn't the smartest idea to pull that out, because I'm going to reuse that and say, well, 10 cubed is 1,000. Oh, actually, I can. Let's take advantage when we can. Before that, 10 divided by 2 is 5. So I have 5 cubed. There we go. That wasn't bad. And 5 cubed is 125. But note how many different roots I could have taken to get here. Look at this. I could have taken that as 10 cubed is 1,000. 2 cubed is 8. So we got 1,000 divided by 8 is 125. I happen to know that 125 times 8 is 1,000. So we could have done that. I could have not done this right here and taken the square root of 100 and got 10 and got 2 and then had 10 cubed over 2 cubed. So any number of ways to get there, and they all work. So you don't have to stress too much about it. Let's do another example with some rational exponents, but we're going to kind of take it in a different way, or doing a couple different things. What if I have 5m to the 4/3 over n to the 2/3 raised to the 2, so squared, times m to the 4th over 8n to the 5th. And raise that to, why not, 1/3. Well, if you thought it was easy, now we just made it a little more complicated, didn't we? Okay, if you didn't think it was easy, sorry. All right, but remember, mathematics, it's doing the steps. Taking one step at a time. Don't look at the whole thing and get overwhelmed. It can be overwhelming when you look at this whole thing, but don't do that. Take it a piece at a time and look at it. And I see a number of things going on here. First of all, I see that we've got this common denominator here, 3 and 3, so we're going to be taking the third root of both of those, right? But I also see this exponent. Well, if I'm going to work my way through this, shouldn't I just bring this exponent in? Can't I distribute that through? So I can make this 5m to the 4/3 squared over n to the 2/3 squared. And I'm going to do the same thing here, times m to the fourth to the 1/3 over 8n to the fifth to the 1/3. So it's a start. Now that I have that, I can bring this in, I can distribute it through, so I can say that's 5 squared times m to the 4/3 raised to the 2. And the bottom just stays the same on that one, n to the 2/3 raised to the 2. And these just stay as they are, so I'm just going to write them down quickly. M to the 4 to the 1/3. And, well, actually, this one, we have to split up, right? 1/3, so 8 to the 1/3. Just trying to make my 1/3 actually look like 1/3. Times n to the 5th to the 1/3. Now, I should warn you here that this is a very common mistake when people start distributing this in. They forget to distribute it to the constant or the coefficient, right? We have a tendency to look at this n to the 5th and say, oh, we need to bring this into the n to the 5th. We forget that that also gets distributed through. Remember, a times b to the n is equal to a to the n, b to the n. Whether a is a constant or a variable doesn't matter. So we have to remember to bring that in. That's what we did here. The 2 went to the 5 and to the m to the 4/3. The 1/3 goes to the 8 and to the n to the 5th. Okay, well now we can start bringing these through. So might as well do this at the same time. 5 squared is 25. 25. M to the 4/3. Remember, we have a power raised to a power. You multiply the powers, so that becomes m to the 8/3. M to the 8/3. We have n to the 2/3 raised to the 2, so we multiply the powers. N to the 4/3. M to the 4th to the 1/3, that's m to the 4/3. And then 8 to the 1/3, that's the cubed root of 8, which is 2. N to the 5th to the 1/3, 5 times 1/3 is 5/3. So n to the 5/3. Well, now we're multiplying these together. We can do that. And that puts us, and I'm going to move over to the side here. I'm going to change colors just so it's more distinct. I'm going to grab my eraser, which fell to the floor. There we go. So we're going to get this out of the way. And well, that can be rewritten as 25 times m to the 8/3, m to the 4/3 over n to the 4/3 times, in fact, I'm going to bring that 2 out front, so 2 times n to the 4/3, n to the 5/3. Now, we have the product of the same base with different exponents, so we add the exponents, right? A to the m, a to the n is equal to a to the m plus n. So we can do that right here. So we have 25, 8/3 plus 4/3 is 12/3. So m to the 12/3. And we have 2 times n to the 4/3 plus times n to the 5/3. So we have 4/3 plus 5/3 gives us 9/3. N to the 9/3. And some of you might be looking at it going, oh, well, that worked out nicely. Because can't we reduce that? We can reduce rational exponents. If they're able to be simplified, then by all means, do it. Sorry, I'm going out of frame here. So if we do that, 12 divided by 3 is 4. So that's 25 m to the fourth, n divided, 9 divided by 3 is 3, so over 2 to the n to the 3. So 25 m to the fourth over 2n cubed. So wasn't that fun? I don't know, you may say that it was not. I may say that it was not, depending on the day. But look at how much we did, and that can be a little intimidating, but at the same time, look at the fact that each little step was just using one of the rules that we knew. We started out with this monster, and the first thing I did was I just distributed through the exponent, so it was in the numerator and the denominator. Distributed through the exponents in the numerator and the denominator. Then I distributed those exponents through if we had a product in there. So I made sure that I raised each of those to that power. Made sure that I raised each of both of those to that power. Then I just used the power rule, or if I had a number, performed the operation, 5 squared. 2/3 times 2 gave me 4/3. 4/3 times 2 gave me 8/3. So the same thing, so I just went through and took that step. And then I said, well, wait a second, commutative property, doing the multiplication and everything, I can move these around. Now I've got something that I can just hit our basic product rule, and I added them to the exponents together. When I got to that point, I said, well, wait. Those rational exponents can be simplified. And when I simplified them, we came out with this. So we started with this, which looked, shall we say, not good. And ended up with that. That's the power of mathematics. And that's where I say it gets fun. It's not necessarily that it's fun, but there's that sense of accomplishment when you take something like this and turn it into that. And it's all just using these basic rules over and over and over again. So just make sure that you pay attention to those things. Now, let's try something a little bit different. And this is factoring when you have negative exponents. So factoring expressions with negative or rational exponents. I should say either or, right? So if I have 28y to the negative 5 plus 21y to the negative 2. And I say factor. Well, what's the first thing you're going to do? You're going to look for the greatest common factor. And that may be a little confusing in this. You can obviously see 28 and 21. I'm going to be able to pull out a 7. They both have that common factor of 7. So that's pretty straightforward. But what about these y to the negative 5 and y to the negative 2? What's considered common? The general rule, if you have negative exponents, is do the bare minimum of what is necessary to make those exponents non-negative. And what do I mean by that? I mean, if I pull out y to, this is y to the negative 5, this is y to the negative 2. If I take out y to the negative 5, then I'm going to be left with y to the 0, right, or 1. If I take out y to the negative 5 here, I'm going to be left with y to the positive 3. So this one got to y to the 0, this one gets to y to the positive 3. So so look for your most negative exponent is probably the easiest way to look at it. Look for your most negative exponent, and that's what you want to take out. So I have y to the negative 5 as my most negative exponent, which is going to leave me with 28 divided by 7 is 4. And that leaves me with, if I take y to the negative 5 and divide it by y to the negative 5, I get 1, right? And then I get plus 21 divided by 7 is 3. And then y to the negative 2 divided by y to the negative 5. Remember, when you divide, you subtract the exponents. Negative gives you y to the negative 2 minus negative 5, which is y to the negative 2 plus 5, or y to the 3. And that's how we can factor if we have negative exponents. We're going to look for the most negative exponent and pull that out, and then the difference between that's going, I shouldn't say the difference between, well, I can say that, but the difference between that is going to be what your exponent is. Negative 5 divided by negative 5, that's, or y to the negative 5 divided by y to the negative 5 is going to give me 0, y to the 0. Y to the negative 2 divided by y to the negative 5 is going to give me a positive 3, y cubed. So look at it a couple times, think about it, but basically you're just pulling out the most negative, and that's going to turn that into the variable to the 0, and it's going to turn any other ones into a positive exponent. So that's how we would factor that. We're trying to turn this into a positive, well, I should say we're trying to turn this into a polynomial. Because remember, this is not a polynomial. Why isn't it a polynomial? Because the variable has a negative exponent. So basically, we're factoring out whatever's necessary to turn this into a polynomial. So that's if we have a negative exponent. What if we have radical exponents and we want to factor out maybe a negative radical exponent? So what if we have x plus 3 to the negative 1/5, just want that to actually look like 1/5, minus x plus 3 to the 3/5. Well, we see that we have the same base. Remember, that is very important to us, that we want to have the same base, because if we don't have the same base, we're going to be in trouble. So that's very important to us. So we see that, well, what can we do? We've got x plus 3 to the negative 1/5, x plus 3 to the positive 3/5. Well, we want to pull out whatever's going to get us positive, right? So this is negative, so that's the highest I'm going to do. I just need to pull out this negative 1/5, because that's going to get it to x plus 3 to the 0. And then I need to do the same thing over here. So I can pull out x plus 3 to the negative 1/5, which, again, that leaves me with 1. And then minus, well, if I pull out x plus 3 to the negative 1/5, I need x plus 3 to the 3/5 divided by x plus 3 to the negative 1/5. 3/5 minus 1/5, or I should say minus negative 1/5, gives us 3/5 plus 1/5, which gives us 4/5. So x plus 3 to the 4/5. So now we have a polynomial, not quite written as a polynomial, but we have a polynomial, and we pulled out the part that had a negative exponent. So different pieces that we can do with that. Remember, your goal is to make it so that whatever's left has non-negative exponents. That's all you want to do. Just make sure that this has non-negative exponents. Don't go beyond that. If you've got negative 1/5 here, don't pull out negative 2/5 and make this x plus 3 to the 1/5. Don't do that. There are times where in solving rational expressions you may want to do things like that, because you may be able, if we had done that, then this would have turned into x plus 3 to the 1, 5/5 or 1, which may help us later on. But when you're factoring it, don't do that. Well, let's get into something a little different on that. What about factoring a rational expression which has negative exponents kind of built into it a little differently? What if I have x to the negative 1 plus y to the negative 1 over x to the negative 1 minus y to the negative 1? Well, now what do? Well, let's play with it a little bit. How can we simplify this? What does the negative 1 mean? It means take the reciprocal, right? So be very careful here. You can't just cancel out the negative 1s. You can't go, well, that has negative 1, that has negative 1, that has negative 1, and just make this x plus y over x minus y to the negative 1. You cannot do that. You can only distribute through division or through multiplication, not through addition or subtraction. So we take the reciprocals, and that gives us 1 over x plus 1 over y over 1 over x minus 1 over y. Well, that's a start. Well, what do we want to do from there? Well, let's get a common denominator on the top. So common denominator would be xy. So we have y over xy plus x over xy on the top. Well, what do we do on the bottom? We can do the same thing on the bottom. And we get y over xy minus x over xy. Okay, now this came out to something a little more interesting, because at this point we have this common denominator all the way throughout this. So at that point we can cancel those out. I'm going to rewrite it one more time and then go through 2 more steps just so it shows exactly what's going on here. But we can say that's y plus, well, put it in alphabetical order, right? Commutative property of addition. Y plus x is the same as x plus y. X plus y over xy all over y minus x over xy. Well, that's a complex rational function, so we can turn that into division. X plus y over xy divided by y minus x over xy, right? Turn that into multiplication. It is equal to x plus y over xy times xy over y minus x. xy, cancel those. Then we get x plus y over y minus x. And there's one more thing that we could do if we decide to go that way, is maybe you don't like the fact that you've got x plus y here and y minus x, maybe you want x to be first. Remember what you can do when you have something like that, can't you pull out a -1? And that will swap those. So we can say that's equal to negative x plus y over x minus y. Because if we multiply through by -1, we get negative y plus x, so x minus y, and we can multiply the whole thing by -1, and that's the same as multiplying by 1. So we can work our way through it. Just be careful of the common mistake, which is to see all these exponents the same and go, oh, we can just cancel that out. Now it did, in the end, turn out very close, but notice it did not turn out the same. If we had canceled these out, I'm going to put this in red because it's wrong. If we had canceled these out, then we would have had x plus y over x minus y. But when we put it in that order, going through all the correct work, we had a negative sign there. So if you'd gone through and just said, oh, I can cancel out all those exponents, you just got off by a negative, which means your answer is completely and totally wrong. So take the steps, work your way through it. Be careful. It's a very common mistake for people to see, oh, same exponent, I can just distribute or pull that out. Other common mistake, and I'll do this in red also. So let me put these back here as they were. -1, -1, -1, -1. Other common mistake is for me to go, oh, well, that's x plus y over x minus y to the -1, which means it's x minus y over x plus y. And again, we see that that is completely and totally wrong. So just be careful of those common mistakes that people make, because we get used to doing certain things and we forget, oh, distributing does not work over addition or subtraction, it only works over multiplication and division. So go through the steps. It may seem like you're causing yourself a lot of extra work, but what you're doing is you're actually getting it done correctly. Little steps, work your way through it. Don't get cancellation happy. Oh, look, I can do all of this, because maybe you can't.